So I think that we have seen that M1, M2 Bayes theorem and all. I just have to go to, we have talked about, I think, at last time what we were trying to see. Okay, I think we were here when I have said that that we wanted to actually find out that what is the KL divergence of this QZ probability of Z given X. Why? Because we wanted to estimate probability of Z given X. Then I have said that because of the same marginalization, probability of Z given X is not easy. So I have said that instead of statistically computing probability of Z given X, I wanted to approximate using another distribution probability of Z, and I want that this probability of distribution, probability of Z, this distribution Q should have to be as close as to this distribution. So that is why we started to say that what is the KL divergence between both of these things. So which essentially comes out to be this, and later using all this stuff we have seen that it becomes a log of probability of X, then the KL divergence between these two things, and then this. So here what we have said is that this particular thing we have said that it's actually the lower bound, evidence lower bound, that is called as the ELBO. So we have got this log of Px, which is for a particular batch or for a given X that you have in your hand for your current iteration, it is fixed. So because of that, log of Px becomes fixed, and KL divergence is anyways going to be a positive quantity. So that is going to be, so this whole thing A plus B, B plus C, this B and C, both of them, addition of that is actually going to be a constant. So if I wanted to minimize this, it's essentially maximizing the ELBO. So once I maximize the ELBO, the corresponding function that we are looking for, that is also going to be maximized over your whole data set. Over your whole data set, it also, the probability of X is also going to be maximized over the given X, whatever the data set over which you are working for. So maximizing C is equivalent to minimizing B, fine, which essentially mean that maximizing C is also somehow increasing the value of probability of X given a particular data set. Up to this we have seen. Now let us redraw the diagram of our variational autoencoder. So first thing that you have to understand is that now our work is going to be somehow maximize the ELBO. Now we wanted to maximize our ELBO. So we understand that we wanted to somehow estimate probability of X, and ELBO, if we maximize ELBO, then it's also going to maximize our probability of X given a particular data set. So from here, let's try to see this autoencoder again, variational autoencoder. You have this X. This is the thing that you are going to get. In between there is coming a network. I say that this is my encoder network. This is actually a mapping network which will take an X, going to give me a Z. Then I have said that wait, I don't want X, I don't want Z. Instead of that, please give me the corresponding distribution parameter from which this Z is coming. Fine. And this network is parameterized over phi. So this is the phi set of parameters that you want your encoder network to somehow understand and learn. This is the corresponding distribution that it predicts. From that distribution, I have sampled something. Using that sampled thing, I passed it to my encoder. Encoder is again a network. This is a mapping network. Again, it's being parameterized over theta, and it will take an X and it will take a Z and generate an X for me. What is your expectation? Your expectation is that the distance between the X predicted and the X that I have given should have to be minimized. And the second, this was the reconstruction loss. And the second thing was that the KL divergence between this distribution and unit normal should have to be as less as possible. This was a diagram. So from this we have started. Remember that now we are going to see our ELBO, and ELBO should have to be somehow reduced. Let us see that suppose that this is my elbow. Elbow is going to be parameterized over theta comma phi. These are two set of parameters. First for the decoder network and the encoder network. The corresponding inputs are going to be x for the decoder, x for the encoder and z for the decoder. And if I say that this is my reconstruction loss and this is my KL divergence, if suppose that my elbow is equal to this, I think that we will be satisfied because this is the thing that we are doing. Our autoencoder, variational autoencoder is somehow minimizing the reconstruction loss as well as the KL divergence. Clear to everyone? Now you see that if I maximize elbow, it has to be somehow related that if I maximize my elbow, my reconstruction loss is getting decreased as well as my KL divergence is getting small as possible. So if I say that this is my KL divergence and this is my reconstruction loss, we are done. Now just you check here that what it is doing. Here you have got a Q distribution. This is, by the way, I am going to show that our elbow is actually this. But just first to see that if whatever I have written here, what does it mean? Here I am saying that the KL divergence between a QZ P of Z, which essentially means that the KL divergence of PZ with respect, the KL divergence of PZ with respect to this QZX. This is the KL divergence. What is written over here? We will talk about this again. And what is this? Fine. But my point is that one should have to understand that what is written over here. Then we will prove that our elbow is exactly equal to this. Okay, fine. So first, this KL divergence is exactly same. We do not have any problem with this KL divergence because it's exactly being written like QZ and PZ. Here I am saying that this PZ is actually being fixed, chosen by us and fixed to be equal to a tractable distribution. We are fixing it. That's this distribution should have to be a tractable distribution. Remember that what was QZ? QZ was a distribution that we have said that it is going to be approximating the probability of Z given X. Now I am saying that QZ distribution has to be as close as possible to another distribution that is PZ, and I am fixing that distribution to be as a tractable unit Gaussian. So this is exactly the thing that we were doing in our variational autoencoder for the KL divergence part. What is this? So if I say what is this, and exactly it is being written. But before that, if I wanted to maximize my elbow, which is written over here, maximize this elbow, then one should have to maximize this and minimize this. Is this okay? If I wanted to maximize my elbow, I have to maximize this and minimize this. Clear? So we are minimizing this thing. This is okay. Fine. We are minimizing. What is written over here? This reconstruction term. This is actually the log likelihood of X given Z. What does it mean? Log likelihood of X given Z. What is the probability that if I give you a Z, you are going to give me an X? What is the probability that if I give you a Z, you are going to give me an X? Who in our network is responsible for this? Decoder. Now you wanted to say that decoder, look, if I give you a Z, you have to give me an X. And I wanted to maximize this probability. That is why it is log likelihood and it has to be maximized. Yes? But these Z's are coming from where? Are they coming from anywhere? No. They are going to be coming from this. And who is this? This is actually your encoder. Encoder is a function which will take an X and give you a Z. Just check it again over here. This is your encoder Q, which is being parameterized over phi. It is going to get an X. It has to give me a Z. Now the decoder should have to be trained in such a way so that whatever the distribution from which encoder is giving multiple z's, whatever the distribution from which it's giving, if I take something from there, I got a new z. Given this z, I should have to generate an x. I should have to maximize this probability. But z's are coming from my encoder, which is written over here. It has to be coming from my encoder. Fine? So when I say that I give you a z, you have to maximize the probability by which you generate an x. It has to be checked with respect to a given lot of data. What is that? It has to be averaged over a particular data. It is going to be averaged over what? It's going to be averaged over whatever I am getting from my encoder itself. And that is why you can see that this is the expected value of this log likelihood, which is being averaged over this. If I maximize this, it only ensures that reconstruction loss is going down. If this goes up, basically that is the log likelihood, this is going high, we are maximizing this, essentially the reconstruction loss is going down. If I give you an x, you will generate a z. Using that z, if you feed it to my network, you are going to get an x hat, and x hat and x should have to be very similar. This is the definition of somehow being seen as the reconstruction loss. You can realize in a different way. Then you will say that, sir, this is actually a log likelihood maximization. Yes, that's a log likelihood maximization. You wanted to do log likelihood maximization in order to maximize your ELBO. Log likelihood maximization can be realized via reconstruction loss minimization. But you can come up with some other thing in which you will say that no, I do not wanted to do x minus x hat and L2 loss of that. That we used to do in our variational autoencoder. X minus x hat dash, x minus x hat and the L2 loss of that. We wanted to minimize that. You will say that I wanted to have some other type of reconstruction loss. No matter. Unless you are able to somehow maximize this thing, there are multiple ways by which you can maximize this thing. One way is that trying to do that via reconstruction loss. Let us see. So maximizing this term ensures that z should have to be generating x's. But these z's are coming from an encoder. Hence it's being averaged over this thing. Remember. It's being averaged over this thing, not over any type of z. Because z, that's a vector. If it's a d-dimensional vector, then it's actually coming from Rd. We are not interested in that Rd. I am only interested in those z's that my encoder is giving when I am showing some x. From where this x is coming? X is coming from our data set. Clear? So, if we have understood this loss, now let us start from that point where we have left in our last lecture, that our L, that is the ELBO or the evidence lower bound, that was actually QZ log probability of x divided xz joint probability divided by QZ. This is the thing that we have got in our last lecture. And you understand that z is nothing but it's actually coming from this distribution that is being expected or being encoder is responsible for, whatever the encoder is giving us. Now this is equal to the quadratic QZ log of this thing. This is the joint probability. Joint probability of x comma z is equal to the, first I will say that what is the probability by which x given z, and then what is the probability of happening of z. This is the joint probability divided by QZ. Straightforward joint probability formula. This is equal to summation QZ log of probability x z given x and summation QZ log PZ QZ. Yes, straightforward mathematics. We have separated both of these things. Now what is this? First term. This is the log likelihood averaged by QZ. Log likelihood averaged by QZ. Similarly, what is this? That is the negative of K1 divergence between QZ and PZ. That is why we have written here that our A term is this, our B term is this. What is our A term? That is the expected value of log likelihood of this, which is being parameterized via theta. That is our P distribution. Who is going to govern this? Our decoder. And this is our encoder, which is saying that I am responsible for giving you Z's from X, and decoder is responsible to generate X's from these Z's. And we will say that if I give you a Z, you make an X. If I give you an X, you make a Z. From that Z, you again make a X, and say that the difference between them should have to be somehow minimized. That is the average value we wanted to somehow minimize. That is the log likelihood of X given Z averaged over X's sampled from this, our encoder. This is actually the maximization of the KL divergence. So if we minimize this KL divergence, that will ensure that QZ moves as close as possible to our unit normal distribution. And why? Because we are setting this PZ, fix this distribution to some known and tractable distribution such that this. Now this is ELBO for you. If I maximize this ELBO, which essentially means that I should be maximizing A and minimizing B. And if you do that, then your ELBO is actually maximizing. Your ELBO is maximizing. The probability of X is also going to be maximized for a given data set. And you started to get better and better estimate of your X's, the distributions from which this X is actually coming. And if you got that, then in that space, if you sample something, some Z, so basically you are not directly estimating X. You are estimating the probability, some probability which is very close to unit normal, and from there you can sample and show it to your decoder. And your decoder started to make images which are very similar to X's. So still there is one more thing that ELBO has. So this is actually the ELBO. You wanted to maximize ELBO, but why we wanted to see this ELBO as a loss function. So one thing is maximizing, other thing is minimizing. You want to make it a function which you wanted to minimize. So from this maximization, we converted it to such a way so that it becomes a minimization. So one is maximized and other one is minimized, and ELBO is on its own getting minimized. Now let us see that what is this. We just have talked about that this is the log likelihood averaged over Q phi Z given X. So that is the likelihood of X given Z averaged over Z sampled from this. So we understand that you have got an X. From that we are going to get this X hat, and let us see it in this way that I have got an X. From that I have generated a Z, and from that I have generated a X hat. So here you are saying that probability of probability of Z given X. Here it is probability of X hat given Z. You want this X hat given Z to be as close as to the probability of X given Z. So it effectively what it becomes, from X you are generating another X hat. So essentially the probability becomes X hat given X. Now what is the probability that if I give you an X, what you are going to give me? That is why it's actually an autoencoder. That is why it's actually an autoencoder. Why it's a variational autoencoder? Because Z's are not fixed. You keep on doing this sampling from some distribution. Now the point is that if I assume the probability of this X, again I am assuming this probability to be some Gaussian probability distribution. Here's the Gaussian probability distribution. This goes, basically that's actually the probability. If I take the log of both of this side, that is the log likelihood. That is actually the likelihood. This is the log likelihood. That is what I have said. That now I wanted to say that expected value that I have just shown, I wanted to maximize this it can be realized in multiple ways. One way of realization is that I wanted to maximize this, so I wanted to minimize the x minus x hat thing. So that is why I have said that suppose that this probability distribution is actually the Gaussian distribution. If I take a log, which essentially becomes this. Now this is your MSE. This is the MSE, because we have seen that the log likelihood you wanted to maximize, then the minus of this you can minimize. Yes? E power minus L2. If I take log, then you will get minus L2. If you wanted to maximize log likelihood, you have to maximize this B term and you can minimize this term. That is the MSE that is getting minimized. Now both of these things, if you see your final VAE loss. Your final VAE loss is the ELBO that we used to say, but that ELBO is being realized in such a way so that this remains to be the same. You are minimizing. But this, that was the log likelihood that you was maximizing, but now it becomes the MSE that you wanted to minimize. This is the thing that we are doing in our VAE. Clear to everyone? This is being averaged over Z, sampled from the distribution predicted by this, your encoder, fed back to the decoder to get your X hats. This was the final loss function that we have got. So actually what happened that we have started from so many things. I have summarized each and everything. Let us see it slowly one by one, this whole recap that what is happening inside. And this thing is also being uploaded on Moodle, and I think you probably have also got this thing. So let's start one by one. First we observed that estimating probability of X directly is intractable. Because your probability of X is this. You cannot do that. Then we try to estimate our probability of X indirectly via latent variable Z. But that too observed to be intractable. Why that too observed to be intractable is that because your probability X, then we have said that no, the dimensions of the X's are very big. So I've said that can we find out this joint probability distribution, but it again has to be marginalized over all of your Z's. And again we have said that sir, it's not possible. So again it becomes, hence this marginalization estimation is also not feasible. Then later we tried to estimate the probability of X via probability of this thing, Z given X. Which again we have seen that the probability of Z given X divided by the probability of X. And again you have to marginalize with respect to your Px. So again your Px marginalization created a problem for you. Then we have decided to approximate this probability via another probability density function Qz, which is actually very close to probability of Z given X, and it is coming from a tractable family. That is why we have written that the argmax of the KL divergence this and this, but Q's it has to be coming from a tractable family. So we now wanted to get this got hold of this Qz. Then the minimization of above KL divergence, the minimization of this KL divergence of Qz and probability of Z given X has to be observed to be equivalent to maximizing the ELBO. This we have seen that once I have shown you that this distribution KL divergence Qz P Z given X, it actually boils down to this thing where this is actually the ELBO. Then we have said that since this is constant, if you wanted to minimize this, that we wanted to do, minimize this, which is essentially equal to the maximization of this. Maximization of this is also going to be helpful when meaningful, because it's also going to somehow boost the value of your probability of X for the given full data set. So instead of minimizing this, we moved to maximize our ELBO. ELBO maximization is equivalent to be the KL divergence minimization between this and this log likelihood expectation maximization. Log likelihood maximization. Then we have seen that that's actually the thing that I has written, that A and B. Your this expected value is here, your KL divergence is here. If you wanted to maximize this ELBO, you have to maximize this value and minimize this value. Fine, we also understand this. Then it comes that fine, we are okay and we are okay with this KL divergence, perfectly fine, but we are not okay with this. We cannot see our MSE thing coming over here. We understand that you will have to somehow maximize the log likelihood over the z's we are getting from our encoder. How to ensure that? So let us rethink that this expectation of log of p theta x given z, this maximization is equivalent to minimizing this thing we just have seen. The maximization of this particular log likelihood is very similar to the minimization of x minus x2. We just have seen that x to z, we can find out this log probability which can be equal to this using a transitivity, and once this we have assumed that x hat comma x probability of this we assume to be a exponential function, that's a Gaussian type of function. Over that if we apply log, then you are going to get this. So essentially if you wanted to maximize this, you can minimize this. Once you understand, finally the loss function of VAE becomes the minimization of this as well as the minimization of this. So this is actually the loss function. Final VAE loss function, you find out the KL divergence as well as the reconstruction loss between the real and the generated image. Once it is done, what is our final story? Our final story, which is about to finish, is that let us assume that we have our observation as our MNIST data set. Our observation is our MNIST data set. We have observed an MNIST data set. It's actually a huge and varying data set. Huge amount of images are there. Huge amount of variation is going to be there. Hence the images X which are there in my data set must be following a very, very complicated distribution probability of X. Very complicated distribution. Now using encoder, we somehow try to reduce the dimensionality of our X. Basically, we wanted to get Z's, the latent variables, so that the reduced dimensional latent vectors Z follow some distribution which is tractable. We wanted to reduce the dimensionality, fine. We wanted to reduce in such a way so that now the Z's that we are going to get, they should have to follow a particular tractable distribution, as well as we can use those Z's to generate our X's back. Subsequently, we train a decoder network that can sample the latent vector from the Gaussian distribution and generate images very similar to MNIST. That is why there are two types of losses. First one is actually the KL divergence, other one is the reconstruction loss. Finally, after training, encoder is discarded. Encoder is completely discarded. And we just need to sample Z's from unit normal distribution. You sample anything from unit normal distribution and feed it to the decoder that will generate novel or new images similar to MNIST dataset but not already present in it.